Okay, hi again everybody. This is Zahida Hosein. This is our second video on momentum force with a few more advanced questions that were previously shown. Um, students had asked me to just quickly go through a few things with regard to this. So this is actually a worksheet given by me, and in doing so, we want to go through a few key points here. At all times, remember we said in our video that we should always identify what the pivot is and the line of action of that force for all forces in our question. The purpose of a pivot, just to recap a few things. If this is your pivot here, for example, as seen in your question, your force is taken at a perpendicular distance from that pivot. So what do I mean by that? Where the pivot is 5 meters away horizontally, you have a duck. We call him Donald for now. Vertically placed and of course vertically downwards is this duck's weight. We call it that particular force 10 newtons. At all times, your force and your distance should make a 90 degrees. Alright, so just point to note, how do we actually, and I know this question did not ask us to identify the clockwise and anti-clockwise moments, but for part A and B of number 1, we will still identify those so that we can use them for the questions that are upcoming. So how do we work out moments of a force here? Just to recap, moments of a force is given as the product of an object's force and its perpendicular distance. Of course, this is part A, right? Now we have the force here given in newtons. An important point to remember at all times, please make sure that your distance is in SI units, which you will see coming down that when they are not in SI units, we must always convert so to SI, of course. So our force being 10 newtons multiplied by, of course, by our distance of 5 will give us therefore a 50 Newton meter moment. This is the moment of a force, the turning effect of a force. So this 10 Newton force will actually turn. What direction will it start to turn? How do we work out direction? Well, you hinge or you place, you can use a ruler or pencil, etc. You place it at this where this distance is, where it mimics your ruler or meter rule, whatever object this duck is standing on, and you place your finger, the tip of your finger, at your pivot. That is your fixed point. So that should be your only fixed point in your question. And you exaggerate that downward push of that force, that 10 Newton force. If that is the case, the entire object will go this way. What way is that way? Well, that's a clockwise direction. So this being a this is my mistake. This is an anti-clockwise direction. Some people write ACW, some people write AC for anti-clockwise or counterclockwise as also called, but this is also an anti-clockwise direction. So your turning effect is also going to be, going to be 15 Newton meters, but in an anti-clockwise direction. All right, we're going to keep identifying each of these. All right, now moving ahead, and of course I'm just going to change the color here, and just for us to pay attention to, we have another example, of course, which is B, and I'm doing the questions here right next to the sheet itself, or next to the questions, the solutions next to your questions, so that you can have a better idea of what you're looking at. Once again, the distance is taken from the pivot, and we have our force acting vertically. Our distance and our force creates that 90 degrees. Hence our definition or formula that moment of a force is the product of a force on an object's perpendicular distance. Alright, so our force here is given as 75. Our distance is of course 12 newtons. So we got a value of 900 Newton meters as the moment of our force. So the turning effect of that force is going to be 900 Newton meters. But what direction will it turn or change? Once again, you place an object that mimics your pivot, well, that mimics your platform, and you place a finger so at your pivot and exaggerate that motion of the force, that downward push of the force. The object is going to go this way, like the hands of an analog clock. So this is going to be a clockwise direction. Now notice I had mentioned the symbols last day and what, of course, the principle of moments are, what CW and AC is, what they represent, sorry. And of course, the shortened version of saying clockwise and anti-clockwise in the previous video. Alright, so here again we have another question where number 2, taking it up a notch. This is where our identification of our clockwise and our anti-clockwise moments come in handy. Alright, so let's see. We have Garfield and Odie, two very famous characters. Their forces are F1 and F2 respectively. Their distance, again from the pivot, again being your fixed point, it's actually well, those distances, sorry, are actually D1 and D2 respectively. So we are given a question here where we are given those values, and I'm going to put them in right here. I always like to tell students, do a shopping list. You don't have to if your diagram is, of course, annotated or you have your information on your diagram. So 85 newtons, of course, is OD's force or weight. His distance is 60 centimeters, but please note this is in centimeters. Our unit for moment of a force is Newton meter. This should actually be in meters. How do we move from centimeters to meters? We divide by 100. So we will end up getting, you move of course your point 2 spaces to your left, just to recap. So you will get 0.60 or 0.6 meters. We don't know Garfield's distance from the pivot. So how will we apply this principle of moments? And of course, this is very similar to a seesaw. We are not sure if Garfield is actually the same distance away from the pivot. Actually, if you look at their weights, because their weights are different, he should not be the same distance as OD from the pivot in order for them to be in equilibrium or keep balanced. So what do we use? And I always like to tell students, write your statement. Take in moments at the pivot. Of course, our pivot is here because sometimes this is a point from maybe a meter rule, maybe the 10 centimeter mark, well not 10, but maybe the 30 centimeter mark, etc. So taking moments at the pivot, that's one mark, just for us to note how it's actually given. Some of your clockwise equals some of your anti-clockwise moments. This is the principle of moments right here. It is used to solve missing lengths or forces when you're given such questions as this one. Let's keep in mind the principle of moments. Just review to your question from A and B that moments of force is a product of two things, object force and perpendicular distance. Well, let's double check that. Force and perpendicular distance, they form a 90-degree. Force and perpendicular distance form a 90-degree. When I do more advanced GC type questions, you're going to realize that that's an important factor to pay attention to. So our clockwise, we didn't actually establish our clockwise and our anti-clockwise force. And here we go. How do we know which is clockwise and which is anti-clockwise? Well, let's check it out. Now here it is, we have a point, which is our pivot, that fixed point. If you're going to use a pen, a pencil, ruler, small ruler, etc., or a little rule, any object that is horizontal, that we can place horizontally on a surface, and you place your finger at the pivot, let's deal with Garfield's weight first. If we push down where Garfield is, ignoring Odie's weight just for a moment, we are going to realize that this entire ruler or your object is going to turn in an anti-clockwise direction. Hence the conclusion that this force is going to, the turning effect of Garfield's force is going to be anti-clockwise. Similarly, and of course, well, conversely, I should say, leaving your finger at that pivotal point, if you push down and exaggerate Odie's force, downward force that is, and not paying too much attention to Garfield's force, then you're going to find the entire object will now tilt in a clockwise direction. Hence the result that your clockwise turning effect or moment is going to be Odie's. So let's see. We can now substitute in the right place. What is a clockwise moment? The clockwise moment is Odie's force by his perpendicular distance from the pivot. So his force is 85 newtons. His pivotal distance from where his line of action, remember his line of action is where this force is acting, is going to be 0.6. Make sure this is in meters, please. Is equal to 120, which is of course Garfield's force, by his distance that we don't know. I'm just going to put the 1 here. We need to find that value, right? Of course, by multiplication and for calculation purposes, we're going to end up getting D1 as 0. Of course, the two decimal places, 0.43 meters. So let's double check something. He is heavier, isn't he? Garfield. He's 120 newtons. So you would expect that he's a shorter distance away from that pivot for him to actually have the same moment as Odie, who is a bit further off from that pivot and has a smaller value for weight or force. All right. Moving ahead, we have number 3. Here we have a little seesaw situation going on. However, the pivot is not actually, just like before, is not actually at the center. We have two weights, Santana's weight and Narayan's weight. And Santana's weight is, of course, 250 newtons. We are not aware of what Narayan's weight is. We have to find that. We are, however, given two distances. Now, just for labeling for students who are actually doing this in terms of A-levels, and of course GC, CAPE, etc. A lot of times, if our formula has x as a distance, you can also use x here as that distance. As you would have seen in your previous question, let me just go back up a bit, they called it d. It doesn't really matter. Distance is a length, and length is a basic quantity. I'm going to stick to what x is, right? X being an unknown value, or even known value in this case for our distance. Now, this I'm going to call it his Santana's distance, x1 from where he's hanging to the pivot, and Narayan's will be x2. Why am I labeling that? Because I'm labeling it according to my forces. F1 corresponds to x1, F2 corresponds to x2. Now, this is by no means the only way to do this. You can actually call it anything you want. So what we are actually going to start with is our statement. Taking moments, of course, at our pivot, which is, of course, we know we have realized it's not centered. Now, I'm going to write my formula first, sum of my clockwise equals sum of the anti-clockwise moments. And before we go to the question, we need to first figure out, as before, where our clockwise and our anti-clockwise turning effect force of those forces is going to be. So let's do it Narayan first. Let's do Santana, he's hanging off the cliff. So you hinge, or you place, I like to use the word hinge a lot, so you place this as your fixed point, place a finger at at any object that you can use as that could replicate this object that they are both on. And if you exaggerate Santana's force acting downwards, the entire thing will actually, if of course Narayan can be raised, the entire object will actually be moving again in an anti-clockwise direction. So once again, this is an anti-clockwise force. Once again, looking at Narayan and ignoring Santana, just for now, what that is, just to find those directions, the clockwise and of course the anti-clockwise force directional changes. What we're going to look at is if we are pushing down at Narayan's force, notwithstanding that Santana is here, but just not paying too much attention to him, and you keep that pivot fixed with your finger, etc., then your object is going to go in a clockwise direction, like the hands of a clock, an analog clock. So we now have our clockwise and our anti-clockwise movements. We can now substitute in the right place. So I'm going to list it like this, just for showing you, being able to show you something. Our clockwise force is F2. Perpendicular distance is x2. See where I'm going at, right? Again, you don't have to put a multiplication sign. You can actually put a dot in two variables. Our anti-clockwise force is F1. Our distance in relation to that is going to be x1. So what do we get from here? F2 we are not familiar with. Multiply by 2 meters is equal to 250 multiplied by 4 meters. Alright, and of course F2 is therefore going to be, if we look carefully, now this is actually 1000 divided by 2, which is 500 newtons. Now if you look carefully at our distances, it is not something we want to guess, but it's something you can pinpoint. Santana is 250 newtons. He is 4 meters away from the pivot. Narayan is half that distance from that pivot. You would expect, therefore, for Narayan to have the same turning effect and to hence keep an equilibrium, because we have applied the principle of moments, for him to keep be in equilibrium with Santana and prevent him possibly from falling off that cliff, then his force will now have to be doubled if his distance is halved from the pivot in relation to Santana's. So I'll say it again. If Santana's distance is 2 times Narayan's, then you would expect Narayan's force or weight to be 2 times Santana's, for them both to have the same moment of a force in both clockwise or anti-clockwise directions. Okay, here again, we have a very similar situation once again, where we can look at Anna and Ravi having 2 separate forces, and their distances are also in terms of meters, so we don't have too much to do with regard to conversions, but we again going to use that same concept. So what do we do again? Taking moments at pivot. People might think, okay, why am I constantly writing taking moments at the pivot, because when we do the GCE or A-level type questions, or even CAPE questions that actually follow suit, you're going to realize how important this statement really is. All right, so let's see. I'm going to write my formula. Sum of my clockwise equals sum of my anti-clockwise. We need to figure out what is clockwise and anti-clockwise once again. Now you realize that there's a trend. Most people say, oh, okay, so if it's the left, it's anti-clockwise. That's not the case. You look at the direction or the position, sorry, of your pivot. So this is our fixed point, your pivot that is. And if we keep this point fixed and you exaggerate Anna's motion downwards by not paying too much attention to Ravi's just to find their direction, then you're going to realize that Anna is, of course, going in an anti-clockwise direction. So her weight will cause an anti-clockwise turning effect. And conversely, Ravi's weight by pushing down, hinging that pivot, keeping that point fixed, and not paying too much attention to Anna's weight, then he is going to go by exaggerating once again that motion in a clockwise direction. Now, this is all well and fine. We now have some work to do. So here we have our force, which is Ravi's force. How do we know we're going to put this here? Because this is his clockwise moment. He is the clockwise force as a result. By his distance from that pivot, you always double check to make sure it's given from the pivot. Not you find it. It's equal to her weight, which is 500, or force as 515 newtons, multiplied by 0.86. That is, of course, her distance away from the pivot. Now, with respect to that, and of course, with respect to doing this value, we basically multiply, of course, the right-hand side, and which, of course, we're going to get 400. I'm going to break it out because some people had asked about this. 473. So we get, of course, weight by 1.1 is 473, because of course it's by substitution 550 by point multiplied by 0.86. So weight therefore is equal to 473 divided by 1.1. Simple transposing. All right, and what we are going to get as a result of that is 430 as his weight. Now let's stop and check something. Should he have a lesser weight? Well, he is further away from the pivot than Anna. Ravi is further away from the pivot as Anna is. So you would expect, therefore, his weight to be slightly or less, just less, simply because you want their turning effect to be the same. This is synonymous to two children on a seesaw. They're not gonna always be the exact same weight. So in doing that adjustment, please keep in mind that if she is at a lesser distance from that pivotal point, or that center of your seesaw, then he should be, and he is of course a further distance away, then his weight or his force should be slightly smaller. All right, because once again, force and perpendicular distance gives us the turning effect of those two forces, any two forces in fact. All right, so in doing number 5, and of course making sure that we continue to understand what we are doing, choose a color. Right, so once again, here now we take it up a notch. We have 3 forces, and it's perfect because here I'm going to actually draw those force directions. It's not given to us. I'm going to label them as F1, F2, and F3. There is no rule to say that you have to call it that, but I'm just doing that for simplicity. All our distances, you stop to check, are all our distances taken from the line of action of each force to that pivot. Let's check. F1's distance from the pivot is D. That's given to us, no problem. F2's distance, 3 newtons. Is that perpendicular distance from the pivot 0.15? Yes, it is. And of course, that 2 Newton force that we called F3, is that taken from the pivot? Of course it is. So we have all our forces. I'm going to first write my statement, or famous, very simple statement, taking moments at the pivot. Write my formula, sum of my clockwise equals sum of the anti-clockwise moments. And of course, this is where the summation sign comes into play. This symbol here, Greek alphabet, capital sigma. It means the sum of, or the summation of, in mathematics. Now, let's analyze a few things. I'm going to use a different color here. So I once again get an object, ruler for example, your pen will work, whatever you are writing with. Place it horizontal, this represents your platform. Hold down this region here, which is the pivotal point. Let's look at F1 first. Analyze F1. We want to know what direction what effect, what turning effect, or what direction could F1 possibly cause this platform to move. And it means, therefore, if we place an object here, keeping your pivot fixed, right and fixed here. And this is, of course, your pivot. We are dealing with F1. Exaggerate the motion of F1. It's going to go in an anti-clockwise direction. What about F2? Only looking at F2 alone, we are pushing down at F2. Same concept, anti-clockwise direction. But what about F3? Not because, again, as I said, not because it is on your right-hand side is it going to be different. Our position of the pivot is very important. When I do the next video, I will explain a little bit further about that. So, placing your point, your finger at your pivotal point once again, and exaggerating F3's motion if it could possibly move the entire platform, it's now going to go like the hands of an analog clock once again in a clockwise direction. So here we have one clockwise force, which should be on your left-hand side if you write your equation as such, and two anti-clockwise force, which will, of course, those would be the motions caused by those forces. So let's substitute. Going back to change. Right. So let's substitute here. And the thing about it is that our clockwise force, once again, it is 2 newtons multiplied by our distance from the pivot, which is 0.3. We're good to go. Anti-clockwise, let's take F1 first. It's 0.5 multiplied by D, plus we have another anti-clockwise force. And of course that is 3 newtons multiplied by 0.15. No problem. What we will get here on either side, please note, and of course by making the subject formula, this is of course going to be 0.6 is equal to 0.5 D plus 0.45. And we transpose, of course, because of course 0.60 minus 0.45, breaking it down so you can see it, 0.45 is equal to 0.5 D, which of course we're trying to find. So this is 0.15 is equal to 0.5 D. D is equal to 0.15 over 0.5, and we will get D as 0.3 meters. Alright, so D is actually 0.3 meters. It's not drawn to scale clearly, which is the same distance as your clockwise force from the pivot. But as we have noticed, some people might say, well, that can't be right, because how could it be the same distance as our only clockwise force of 2 newtons? But pay attention, this F1 is a very small force. So that combination of that very small force, 0.5, and its perpendicular distance from the pivot, in combination or of course in a summation with F2, 3 Newton force, and a very short distance from the pivot will give us the same turning effect as that one clockwise force F3 on the right hand side. So you always double check your values to make sure that they are correct. What you can do is plug in 0.3 back as D1, multiply it by 0.5, you add it to the product of F2 and its distance, and you should be able to get, and you will be able to get the product of what we had on our left hand side here, of our clockwise force, or clockwise movement more specifically. Okay, and here is our final question. And our final question, once again, has 3 forces, and it's pretty interesting because it is giving us a lot. It gives us a lot of practice in what we need to do. First things first. This is our pivot. It's a nice color diagram too. All our distances from the pivot, from W to pivot, 1.5. Very good. From this 20 Newton force to our pivot, 1.5. Yep. From our 45 Newton force to the pivot, yes. We have all our distances taken from the pivot. All right. So we now need to pay attention. We are going to say again, taking moments at that pivot, what we will get writing my formula one time, sum of my clockwise equals sum of the anti-clockwise moments. And we need to now figure out what is clockwise and what is anti-clockwise. Same thing we've been doing. Take your pencil, a pen, whatever you're writing with, place it horizontally as your platform. Let's deal with W first. Place your finger at the point, that pivotal point, and push down where W is, and you're gonna mimic the situation, right? Pushing down and exaggerating that motion for W is you're gonna realize W is going to act in an anti-clockwise direction if it can cause any turning effect. What about 45 newtons? Ignoring all other forces and only analyzing 45 newtons, the same concept applies. So I'm pushing down on my 45, and the whole thing is actually going to go in a clockwise direction by exaggeration. Sorry, I'm writing anti-clockwise. Let me erase it. So this is going to go, yes, in an anti-clockwise direction once again. Sorry, in a clockwise direction. What am I saying? Once again, and our 20 Newton force, ignoring all other forces, just for us to be able to find our directions, our 20 Newton force acting downwards, and of course our pivotal, that point fixed. If we exaggerate that force acting downwards, it can possibly cause a tilt of a clockwise direction. Alright, so we have, in this case now, we have two clockwise and one anti-clockwise moment. In the previous example, we had two anti-clockwise, one clockwise. Doesn't matter, we can work out anything at this point. So let's substitute. I'm taking my first anti-clockwise force as 45. So 45 multiplied by 1 plus 20 multiplied by 1.5 is equal to our weight, our only anti-clockwise force, should stand always on by itself on one side of our equation, multiplied by 1.5. And of course, by making this very easy and by working them out, what we are going to get, I'm going to go ahead and just write the value here by substitution, weight. Okay, let me write it out for you, for those of the benefit of those who want to see this worked out. Alright. So what we will get is 45 right here plus 30. 20 by 1.5 is 30. It's still 1.5 by our weight. So we will get 75 is equal to 1.5 W. So W is equal to 75 over 1 or divided by 1.5. I'm going to write it up here. Our weight, therefore, will end up being, let's type it to make sure, on our calculator is 50 newtons. So this person's weight is going to be 50 newtons. Alright, so thank you very much. These are just what was requested with regard to momentum of force. Thanks for taking a look. I'll be posting more videos based on momentum of force because our students have mentioned to me it's a big topic that they want a little bit more explained. Feel free to post any comments. You can subscribe if you want more updated videos, and of course we're going to be launching some new experiments very soon. Any questions you want to have answered, please feel free to ask. Thank you very much and have a good day.